In the previous lecture, we were discussing about hypothetical reference sonic conditions. These are reference conditions which could have existed within the flow at a point where the Mach number would have been 1. So, it is a hypothetical reference state. In the real flow, there need not be any physical point where Mach number is 1. So, we would call it hypothetical reference sonic state. So, let us call this as star. So, from mass conservation you can write rho A u is equal to rho star A star u star. Okay. So, now you can write u is equal to what? M into root over gamma r t. These start states corresponding to what? They correspond to isentropic flow. So, if the flow is different from isentropic, the start state changes. This is very, very important. So, this reference state is a given reference so long as the flow remains isentropic. If there is a change in the isentropic nature of the flow, the start state changes. Such a change in isentropic nature of the flow occurs in the presence of a shock wave. So, if you have a shock, we will discuss the shock later on, you will have the change in the reference hypothetical sonic reference state properties. So, u is equal to m into gamma r t. So, what will be u star? U star corresponds to the sonic state, sonic is m equal to 1. So, u star is root over gamma r t star. Okay. So, you have u by u star is m square root of t by t star. How do you get t by t star? Because rho by rho star will also be a function of t by t star. So, you have T0 by T, you have a formula for this, right, T0 by T you have 1 plus gamma minus 1 by 2 into m square. So, you have T0 by T star remember T0 remains constant for an isentropic flow, P0 remains constant for an isentropic, these are very important reference parameters, A star remains same for a given isentropic flow. So, T0 by T star is equal to 1 plus gamma minus 1 by 2 into m square. where m is equal to 1. So, this is gamma plus 1 by 2. So, you can write T by T star so basically you divide this with this. So, gamma plus 1 by 2 by 1 plus gamma 1 plus gamma minus 1 by 2 m square. Is it all right? Okay. So, then you have rho by rho star. So, you have T by rho to the power gamma minus 1 is equal to constant, right. So, T by rho to the power gamma minus 1 is equal to T star by rho star to the power gamma minus 1. So, rho by rho star to the power gamma minus 1 is equal to T by T star. So, rho by rho star is T by T star to the power of 1 by gamma minus 1. So, you have rho A u is equal to rho star A star u star. So, A by A star is u star by u into rho star by rho, right. So, u star by u is equal to 1 by m into square root of T star by T into rho star by rho is T star by T to the power 1 by gamma minus 1. So, this is 1 by m into T star by T to the power 1 by gamma minus 1 plus half, and T star by T is 1 plus gamma minus 1 by 2 m square by gamma plus 1 by 2. This is from here to the power 2. So, this is gamma plus 1 by 2 into gamma minus 1, right. So, this is A by A star. So, we have achieved to write the area explicitly as a function of Mach number referencing to A star. So, if you have a Mach number, you can calculate what is the area. That is how area versus Mach number graph or Mach number versus area graph can be drawn. More interestingly, for a given area, so look into this problem into two ways. One is given a Mach number, you will have an area straightforward. Next is given an area, you will get two solutions for the Mach number, and one of these will correspond to a subsonic solution, another will correspond to a supersonic solution. And when m equal to 1 you can see A will be equal to A star. So, A deviated from A star can give rise to two conditions, which is either m greater than 1 or m less than 1, not m equal to 1, because if m equal to 1 A will become equal to A star. So, to summarize, this is what we have achieved. So, for an isentropic flow, we, for a given m, we know what is, we find out what, we can find out what is P by P0. We have derived the formula, we have derived T by T0, we have also derived, if not we can relate rho with P and T, and we can write rho by rho 0 and we can write A by A star as a function of Mach number. So, all these things, you know, we have analytical expressions, but if you, for a given Mach number, if you put the value in the analytical expression, then the remaining parameter is only gamma, which for air or any particular fluid is a constant if Cp and Cv are constant. So, for calorically perfect gas, it is very easy to construct such a table, where for a particular gas with a constant gamma, for a given m you have these values tabulated, and that is what is done in isentropic flow tables, that you will get accompanying any, so isentropic property tables. That you will get in any book where you are handling compressible flows. Now, once we have these expressions, what we have learnt is how to handle a variable area situation. Of course, we have understood how to handle a variable area situation when the flow is isentropic. We will later on see how to handle the situation when the flow deviates from isentropic, but before that, for a variable area isentropic flow, let us work out a couple of problems. Consider isentropic flow in a channel of varying area. Between sections 1 and 2. Given M2 is equal to 2 and V2 by V1 is equal to 1.2, estimate what is M2, what is A2 by A1 and whether the M1 is 2, not M2, right, because the question is what is M2. So, M1 is equal to 2, yes, you are correct, it is M1 equal to 2. Okay. So, estimate what is M2, what is A2 by A1 and whether it is a converging or a diverging nozzle. So, now let us try to work this out. So, V2 by V1 this is given, this is 1.2, V2 is M2 into C2 and V1 is M1 into C1. So, this is M2 into root over gamma R T2, this is M1 root over gamma R T1. Because it is isentropic flow, what remains constant is T0. So, you can write M2 by M1 root over T2 by T0 root over T1 by T0. T0 by T, the formula is what? 1 plus gamma minus 1 by 2 m square, right. So, this is M2 by M1. So, this will be root over T1 by T0, T0 by T1 will go to the top. So, 1 plus gamma minus 1 by 2 M1 square to the power half by 1 plus gamma minus 1 by 2 M2 square to the power half. So, in this equation what are the things, what are the parameters in the right hand side, M1 and M2. So, you know what is M1. So, from this equation somehow you solve for M2 and that is the first answer. So, M2 is 2.98. Next is what is A2 by A1. A2 by A1 is A2 by A star divided by A1 by A star, right. Isentropic flow, so A star is constant. So, this is function of f of A by A star is a function of m and this is the same function of M1. So, if you substitute these values you will get 2.46. So, this A2 by A1 this is 2.46, but this alone does not tell you about the shape of the nozzle. It is A2 by A1 is just the ratio of two areas. So, to get the shape of the nozzle you have to use that dA by A formula. So, let me write this from my notes. So, dA by A is equal to dm by m into m square minus 1 see m1 is 2 and m2 is 2.98. So, both m's are greater than 1. So, m square minus 1 is greater than 0 and this is greater than 1. So, if you have dm by m, so it all depends on dm by m. So, if dm is, so m1 is 2 and m2 is 2.98, so dm is greater than 0, that means dA is also greater than 0. So, when m1 is increasing from 2 to 2.98, it is increasing continuously, and therefore dA greater than 0 is also happening continuously, that means it is a diverging section. Okay. Let us work out another problem before we call it a day for this lecture. So, you have a nozzle like this with the areas of sections 1 and 2 are given. So, and also these parameters are given. Assuming isentropic flow, what is P1? What is M2? And what is the mass flow rate of air? Let us see first what information we can get about the Mach number at section 1. That is easy to get because we know that you have M1 is equal to U1 by C1 and C1 is square root of gamma r T1. How do you get T1? So, you can apply the energy equation. So, you can write Cp into T0 is equal to Cp into T1 plus U1 square by 2. So, when you know what is U1, this is given, you know what is T0 which is given, from here you can get what is T1. So, once you get what is T1, you substitute it back here and this will give you what is Mach number at section 1. So, Mach number is Mach number at 1 is 0.208. Now, what we know is A by A star is a function of Mach number, right. So, A1 by A1 star, A1 by A star is the function of m1. So, if you know m1, you know this function of m1. So, you will get a1 is pi d1 square by 4. So, you will get what is a star. Now, a2 by a star, a2 you are given pi d2 square by 4 is the same function of m2. So, you substitute this a star from here, a2 by a star is a function of m2, from there you will get the value of m2. So, because it was subsonic, it will remain subsonic in the converging section, right. So, that is why the Mach number less than 1 solution we have taken. So, this is m2 equal to. So, once you know m2, you can find out. So, you have p2 by p0 or p0 by p2 is a function of m2, another function, it is a different function from that. So, you are given what is p2, you know what is m2. So, from here you get what is p0. Then you know p0 by p1 is a function of m1, same function. So, if you know what is m1, which is already know, and you have obtained p naught. So, you see very nicely how a star, p naught, t naught become references to relate to points 1 and 2, that is what conceptually we are doing. So, you will get what is p1. So, p1 is 189 kilopascal and m dot air is rho 1 a1 u1, right. Rho 1 is p1 by RT1. We have already obtained what is p1, a1 is known, u1 is known given, and T1 has also been obtained. Okay. So, you know m dot air, this is 0.313 kg per second. So, to summarize, today we have seen how to handle problems related to variable area ducts in isentropic compressible flow. The interesting situation comes when the flow deviates from isentropic, and one such possibility is that the flow is still adiabatic, but it is not reversible, and that deviation from reversibility very prominently occurs in a condition when there is a shock wave in the flow. So, in the next lecture we will analyze a situation when there is a shock wave in the flow such that the front across which there is an abrupt discontinuity in fluid properties because of the shock is perpendicular to the flow direction, that is called as a normal shock, and we will consider that in the next lecture. Thank you.